Okay, so what I'm going to try to do with these videos is give some very succinct examples of the learning targets or the objectives for this week. Okay, so the first one we're going to do in section 2 is we want to learn how to write limit notations to describe a limit. And now there's some different situations, and these are 3 of them that happen. But and no matter what example, what you're looking at, you see this definition here. You always write the limit as x approaches some value. The c is some value. And then, if you have an equation, you can write the equation, but you can also just say f of x in this case, because they give us a graph. For these examples, they actually gave us the equation. So we could write in the equation here instead of writing f of x, but that's a lot of work. But that's what it is. And it's equal to some value. So if the limit exists, as x gets closer and closer to that number, whatever the number is, y is going to get closer and closer to that value. Okay, so if we look at this function here, what we see is a line, we see a linear function, but there's a hole in the graph, and we're going to talk later on why that hole's happening. But so for the limit, the number, the c number, see how the c number's there? The c number we're interested in is 2. So what I'm going to write is I'm going to try to write this as the limit. Here, where am I going to write this? I guess for a. So we'll write the limit as x approaches 2 for f of x. And as I said, we could write the function if we wanted to. What's happening? So I see as I approach that 2 from either side, it's going in the same value. And what value is that? Well, 1, 2, 3, 4. So that the L in this case is 4. Even though when x equals 2 is not defined because there's a hole in the graph, as we get closer and closer to 2, y is getting closer and closer to 4. Here it's coming from the negative side. Here it's coming from the 3 side. Here it's coming from the over 5 side. So they're both approaching 4. So to write that limit, I would write equals 4. Now this one, what happens? Look what's happening to this one as I approach 2. And these you're going to see these absolute value functions divided by the same thing, just not an absolute value. That always works out to be a horizontal line, 2 horizontal lines, and it's always the ratio of the leading term. But we'll go there later. So what happens here as I approach 2 from the left, it's down here at -1. As I approach -2 from the right, it's up at +1. So do you see how these are approaching 2 different values? So in that case, the limit doesn't exist. So what we would write would be the limit as x approaches 2 for f of x. We could write dne does not exist, undefined. Usually we write dne doesn't exist because I'm getting 2 different values. Okay, then the third one here is pretty interesting because what's happening with that one? Here, let me delete some of this. You should always come back and watch it later and get those down. As I approach 2 from the left, it's headed up here to +infinity. As I approach 2 from the right, it's headed up to +infinity. So there's 2 ways of thought about this. Some people might say, well, infinity, you can never get to infinity, or I guess Chuck Norris could, but none of the rest of us could. Sorry, Chuck Norris joke. So some people might say the limit as x approaches 2 for this function doesn't exist because we can never get to infinity. Some other people, depending on what they want, what the goal for this is, they might say the limit as x approaches 2 for f of x approaches infinity. So it's because on either side, we're both headed to a +infinity. If they were going in opposite sides, like if one side was going up, one side was going down, but they're clearly headed to 2 different values, -infinity, +infinity. So that definitely doesn't exist. This one's a little bit more gray area, and depending on what your purposes are, you can answer it either way. Now, one other limit that can happen is when we're not approaching a value like 2 or 3 or 4 or -2. What we're doing is we're going to say, what happens is I go way, so this is an exponential decay equation with a horizontal asymptote of 1, right? So as I go way out to positive infinity, that function is going to approach 1. In fact, we don't even have to get out to positive infinity to make it. I mean, you can see right here, at x equals 5, it's pretty darn close to 1. So what we'll say in that case would say the limit as x goes to infinity of f of x, that approaches 1, that horizontal asymptote, okay? So this is a limit at infinity. If I had like that graph of when x equals 2, when it was headed like this, that's an infinite limit because it's the y value is approaching infinity. Here, the x value is approaching infinity. So limit at infinity, this one's an infinite limit. I guess that's it graphically. We should go look at some tables of values, tables now. Okay, so for this function here, this is one of those ones that, for now, I'm going to show you. I mean, where we're going with this is we're going to be able to manipulate these expressions to find the limit algebraically. This is the one that we can't do that with, so it's an important one to show you first off, and just say, you know, the goddess of math told us this is what the limit is, so we'll just accept that for now. And later on, once we get a little more math under our belt here, a little more calculus under our belt, I can show you how to do it relatively easy. So looking at the graph, because that's what I was just doing, we can see that when I graph this function, as I approach 0, and that's what I'm trying to find, I guess, is what's the limit as x approaches 0, because that's the problem child of f of x, if f of x is sine x over x. So as I approach 0 from the left, you see how we're approaching positive 1. As I approach 0 from the right, we're also approaching positive 1. So graphically, it looks like the limit is 1. And now if we look at it as a table view, so what I did is I said -1, then I added 1/100th to it, so it's increasing up until, so notice it's not 1 there, but it's getting there, right? I mean, I'm pretty close. But as you see, as I approach it numerically, as I get closer and closer to 0 from the left, it's 1. It's approaching 1, and from the right, it's also approaching 1. So sometimes looking at functions in a table form and seeing where it's headed either side of the value that we want, of the C number, say, that'll help us figure out what a limit is also. So you can do it, especially if it's a messy function. You know, sometimes using tables is the only way to do it, until you learn some other stuff. Okay, so this is an important one. I want you to have written down somewhere or just remember somewhere that the limit as x approaches 0 of sine x over x, that's equal to 1. And graphically and tabularly, we can see that's how it works, okay? So remember that. And so the table, what they do in the homework, they're going to give you some values and get closer and closer to the value using a table. And I did this with a spreadsheet. A graphing calculator also does a great job with it. Yeah, I mean, I guess you can plug them in by hand, but that's who wants to do all that calculation? Okay, so that's using tables, and you'll see that. So this next thing I want to talk to you about is what's a one-sided limit, and I've already kind of talked about that. But when you talk about a one-sided limit, is you just concentrate on one side, and the way you write that notation is this way. So from another person's notes that I really like to use as materials, when you're talking about a one-sided limit, do you see how this has the little plus sign? So limit as x approaches some number c, but the plus sign, that's coming from the right, and if it's a minus sign, that's coming from the left. And he says that to us here, okay? And the L and the K are arbitrary. I mean, you could write L in both of them, but it's because sometimes they're the same. And then we'll talk about this last piece in a minute. So let's go take a look at this graph here. Let's get this off here. So in this graph, I see the break at x equals 2. So that's the issue going on here, right? So that's my breaking point. So what I'm interested in is, what's the limit as x approaches 2 from the left of f of x? So what we do is we ignore everything to the right of it. We're just looking at that linear function. And as I approach 2 from the left, so as x approaches 2 from the left, what is y approaching? And I see it's approaching 1, 2, 3. And then the limit as x approaches 2 from the right, well, let's see. Let me do a little cleaning up here so we can see that. So as I approach 2 from the right, well, here's what's happening to y. What's y approaching? Well, y is approaching 0, right? Now, because the left-hand limit and the right-hand limit don't agree, they aren't coming to the same value, the limit doesn't exist. But we can talk about the limit separately. I mean, the left-hand limit is 3. The right-hand limit is 0. Now, those are valid and those are correct. But when we're trying to say, if I just asked you what the limit is, if I said, what's the limit as x approaches 2 for f of x? Well, that's because the left-hand limit and the right-hand limit don't agree. That's a DNE. Okay, so you can look at it graphically. You can do the same thing with a table, approach it from the left and the right and see it. And when these piecewise defined functions, that's where they get a little wonky, okay? And you can kind of see, maybe we should talk about piecewise defined functions if it's been a while since you've done a pre-calc class or even an Algebra 2 class. Let's see here. Okay, so here's a function. Interestingly enough, it also uses x equals 2 as the breaking point. So when I have to graph a piecewise defined function, I'll usually put a dotted line at the place where it changes. And if there's more than 2 places, I put a dotted line in both of those. And then to the left, I'm sorry, they wrote this backwards. So to the left of the line, we're going to graph the line 3x plus 1. So here, let me go to a blue graph. So 1's the y-intercept. I'm going to go up 3 over 1, up 3, 1, 2, let's see, 1, 2, 3 over 1. Okay, and I'm going to use a dot here, and then I'm going to go down 3 over 1, down 3 over 1. So there's that function here, and I'm going to use a filled in dot because see how 2 is included in the domain of that function? So I use a solid point there. Now for the other piece, I'm going to graph the line. Well, let's see, I'm going to rewrite this so it's in slope-intercept form, negative 2x plus 5. So that crosses the y-axis at 5. So 1, 2, 3, 4, 5. Now I'm going to do this at first, but I'm going to erase this work that I'm doing right now because this function is not this f function is not defined with, I'm not using this piece on the left at 2, I'm using it on the right at 2, but I'm just doing this part so I can get an idea where to start. Okay, so I see if I went down, I started at 5 and I went down 2 over 1, down 2 over 1, I'm going to cross that line x equals 2 right there, and I need to put an open circle there because it doesn't include 2. 2 is being included for the other piece. And it's a good thing because it wouldn't be a function that way, right? If I were to do the vertical line test, it would pass. If those both were filled in, it would pass. It would fail the vertical line test because it would cross in 2 points. But in this case, it doesn't because it's not filled in. So let me erase this. Let me erase my erroneous things that I just drew. Okay, there. Now let me come back and. So then I'm going to go down 2 over 1, down 2 over 1, down 2 over 1. So that's what that right-hand graph looks like. Okay, and this goes down to infinity also. Okay, so now let's answer some questions. This is asking me, what's the limit of this function as I approach 2 from the right? So from the right is from the positive side of 2. So to see how it's this red graph here, so as I approach 2 from the right, y is approaching 1. And as the limit, as I approach 2 from the left, see the little negative? That's going to go up to, oh my, what number is that? 4, and then went up 3 more, so I'm thinking 7. And then what can I say about this limit? Well, see now this one isn't a sided limit. and the limit from the left is 1, the limit from the right is 7, so you're thinking, does this limit exist? If so, I should write a number, or if it doesn't exist, I should write D and E. What do you think? So because we're approaching two numbers, a number from the left is 1, a number from the right is 1, the number from the left is 7, this limit does not exist because they aren't agreeing on the same number. Okay? So that's how the left-hand limits, the right-hand limits, and finding the limit at a number, at a value, all are related. If your limit from the left is not the same as the limit from the right, there's no limit there. It doesn't agree. So one thing that comes up is sometimes they'll tell you what to do, but let's examine this. So what do you think? Where does the limit? I see 3 places where there's issues. So I guess let's ask ourselves, where is the limit for this function defined? What values of x does it have a limit, and where doesn't it have a limit? And we'll only consider this domain, this graph from here to here. We won't consider beyond that because we don't know what's happening there, and I don't even know what value that is. But what are you seeing? Well, maybe it's easier to ask where it doesn't exist. Doesn't it exist? So what I see right here, the left-hand limit is 6. The right-hand limit is 3. So right there, that doesn't exist because the limit doesn't exist, it disagrees. But the left-hand and right-hand limit do. So if I wanted to write that, I would write the limit as I approach 1 from the left for f of x. That equals 6. The limit as x approaches 1 from the right, notice the minus and the plus, of f of x. That equals 3. And then how about the limit as x approaches 1 for f of x? Notice there's no limit. Now there's no left-handed, right-handed limit here. So that's a D and E, right? Because it equals 2 different values. So that's at x equals 1. What's happening at x equals 3? Well, what I see is I see an infinite limit, right? It's headed down to negative infinity on both sides. So 2 schools of thought. You could say, well, let's do the left-hand limit and right-hand limit. The limit as x approaches 3 from the left of f of x, well, that's headed down to negative infinity. And the limit as x approaches 3 from the right of f of x, that's also approaching negative infinity. Now, because these are approaching the same 2 values, you could say if we can get to infinity, we could say the limit as x approaches 3 for f of x, you could say it's an infinite limit of negative infinity. You could also say it doesn't exist. Then I guess the only other issue that really shows up is what happens with that hole. Whoops, let me undo what I just did. There, I'm still recording. So at that hole, what's the limit from the left? The limit as x approaches negative 2 from the left of f of x looks to me like it's approaching 3. The limit as x approaches negative 2 from the right of f of x, well, that also looks like it's approaching 3. So I guess because the limit from the left is the same as the limit on the right, we can say the limit as x approaches negative 2 for f of x is 3, because it's approaching that L number, okay, that value. And then any of the other points here that are on this graph, I mean, because there's an infinite number of points, like what about this one? I mean, I don't know what the y value is, but I see as I go from the left it's a value and right from the value, so that limit exists, and there's no other place where the limit doesn't exist, because it's always defined and it's the same as from the left from the right. Okay? Okay, then another learning intention I want you to have out of this is what's a vertical asymptote? Well, we know vertical asymptotes happen where the denominator, it's a rational function with a variable in the bottom in the denominator, and the vertical asymptotes happen where that value is equal to 0. So see, if I have this one, x minus a, where does that equal 0? At x equals a, whatever a is. And that's that. And then what happens if it's a squared value, or it could be a fourth power value? X can't be that value, but they head in the same direction, so that's where it's a possibility where you could talk about an infinite limit. But this one, you can't talk about an infinite limit because they head in opposite directions. Okay, so that's just all. I mean, if you did my pre-calc class, you saw a lot. We spent some time with the rational functions, so you gotta remember about where it acts like 1 over x squared. Okay, and it's just shifted left or right for this case. Okay, now one last thing maybe. If you look at, so we talked about limits, how they go to different values. Then you get something like this, and what happens is you come from the left, it's one value, and you go from the right to the other value, and what happens, it bounces back and forth, back and forth. If we could zoom in really close to this, it would look something like this. I mean, I don't know if it's coming from the right or from the left, but it would be looking like it's coming down like this and be coming up like this, and it's never going to reach the same value. And that usually comes from when you're dividing by 0 inside the argument. Not always, but sometimes. Okay, so just be aware those oscillations can happen, and fortunately we don't do much with those, but just recognize that they exist. We can't find the limit with those, so we don't really worry about it. We know they exist, but we don't have to work.